Today, we're going to pull back the curtain on something you use every single second you're online, the Internet's digital postal service. We're going to dive into the hidden system that makes it all work. Let's get right into it. Have you ever really stopped to wonder how it all works? How does a message, or a photo, or an email travel from your phone to someone else's halfway across the planet almost instantly? It's not magic, but it is an unbelievably clever system. Well, the secret is all about breaking things down. Your data gets chopped up into these tiny little things called IP packets. The best way to think about them? Digital postcards. Billions and billions of these things are zipping around the globe as we speak. But of course, for a postcard to get anywhere, it needs instructions, right? It needs a to address, a from address, and rules for how to handle it. In the digital world, that whole set of instructions is called the IPv4 header, and that's exactly what we're going to unpack today. Okay, so first things first. Just like any piece of mail, you absolutely need an address. This is the most fundamental part of its entire journey. And here it is. This is our master map. Now, I know it might look a little intimidating at first glance, but stick with me. We're going to break down the most important parts one by one. And what's really amazing is just how much information gets packed into such a tiny, tiny space. Let's start with the most obvious ones. The source IP address is basically the return address. It's who sent the postcard. And the destination IP address, well, that's where it's going. Simple as that. Without these two, literally nothing else matters. They are the absolute heart of getting data from point A to point B. Now, if you look right at the very top of that header, there are a couple of fields that set the ground rules. The version field is super simple. It just tells the network, hey, we're using version 4, IPv4. And the IHL, that stands for Internet Header Length, and it just tells the receiving computer exactly how long this list of instructions is, so it knows where the actual data begins. So what's the standard size for all these instructions? Just 20 bytes. That is it. All the essential information to guide a packet of data across the entire globe fits into a space that is incredibly small. This efficiency is a huge part of why the internet was able to scale up the way it did. So we've got the addresses down. But the internet can be a pretty chaotic place. What happens if one of our little postcards gets lost, or even worse, gets stuck in some kind of endless loop? Well, the header has some really smart safety features built right in to handle exactly that. One of the most brilliant of these safety nets is called Time to Live, or TTL. Just imagine a real postcard getting stuck between two post offices, just bouncing back and forth forever. The TTL is basically a self-destruct timer that prevents that exact problem from happening in the digital world. Here's how it works. A packet gets sent out into the world with a starting TTL value. Every time it passes through a router, which is like a digital post office, that number gets reduced by 1. If the TTL ever hits 0, the router knows the packet is lost and just gets rid of it. And that's so crucial. This super simple countdown mechanism is what keeps the internet from getting totally clogged up with immortal lost packets. It's just an incredibly elegant solution to what could have been a massive problem. Okay, so once the postcard finally arrives, the protocol field is like a little note on the front. It tells the receiving computer what to do with the data inside. Is it a piece of a web page that needs to be assembled perfectly? That's TCP. Or is it part of a live video stream where speed is more important than perfect order? That would be UDP. This field makes sure the data gets handed off to the right application. All right, so we can address our packets, and we can make sure they don't get lost. But what happens when we have special requirements? Like a really, really big piece of data, or something that's super time sensitive.
This is a really common problem. See, different networks all have their own size limits for packets. So what on earth do we do with a postcard that's just too big to fit?
While a single packet can be up to 65,535 bytes, many of the networks it has to travel through can't handle anything near that large. So the system needs a way to deal with this. And the solution is to break it into smaller pieces. It's a process called fragmentation. 3 fields in the header manage this whole thing. Identification is like a serial number that links all the pieces together. The flags field basically tells the receiver, hey, just so you know, more pieces are on the way. And the fragment offset tells the computer exactly how to put the original postcard back together, even if the pieces arrive all out of order. Now, we all know not all data is created equal. Some things are just more important than others. And that's where the DSCP field comes in. Honestly, the best way to think of it is as a priority mail or an urgent sticker for your postcard. And why does that matter to you? Well, this little sticker tells routers all along the path to handle this packet with extra care and speed. It's what makes sure your time-sensitive video call stays smooth and doesn't get all glitchy just because someone else is downloading a massive file. It's quality of service in action. So when you take a step back and you look at all these individual pieces, you really start to see a system that is, well, it's pretty remarkable. Look at our master map again. From the basic to and from addresses to the TTL safety net to the complex rules for fragmentation and priority stickers, all of these fields work together in perfect harmony, and they do it on billions of packets every single second. And that's the real takeaway here. The huge, sprawling, complex thing we call the modern internet is all built on top of this surprisingly simple and elegant foundation. It really is a masterclass in engineering. But this system, IPv4, was designed decades ago. It has a limited number of possible addresses. So, a final question to leave you with. What happens when we run out? When there are more devices than there are addresses in the digital phone book? Well, that is a story for another time. If you enjoyed breaking down the IPv4 header with us and found this explainer helpful, please take a second to click that like button and subscribe to the channel. It genuinely is a huge help for us and allows us to keep making these for you. Thanks for watching.